Hi folks, Mr. Long's back for video number 3 on Intro to Vectors. The next measurement or characterization or observation of vectors we need to look at is the unit vector. So when we talk about unit rate, we say things like you driving at 80 kilometers per 1 hour. So it's a comparison to 1. The unit vector is no different. So what we're doing is we're taking any old vector, okay, here's a vector, and maybe it's called vector W, and maybe it has a length of 6. So what a unit vector does is it will have the exact same direction as the original vector, but only a length of 1. Right? So there. So the same angle, right? If you look at an angle being theta here, for example, the unit vector, which we denote by a cap. Okay, that's a unit vector right there. And a unit vector, again, it always has length 1. By the way, what would you have to divide W by to get the unit vector length? How would you turn a 6 into a 1? Well, you divide by 6, right? You divide by the magnitude. Okay, so a unit vector preserves the angle, but it has a length of 1. Why is it important? Well, unit vectors are very important in physics for one application. So say, for example, you've got a like a what you might call a strut or something. So this is the ground here, and this is a piece of metal right here. Okay, and it's different forces are being applied to it. Maybe it's holding up, or maybe it's just holding up a sheet of metal or something, right? Like, and this would be like almost in 3D, right? It's holding something up here. So there's some force being pushed onto this, okay? But this object here, say, it can be varying weights, okay? So this right here is like it's just holding this box up. So this can have different weights. So the force in this will be different. But will the angle ever be different? So all we do is we get a unit vector for the direction, right? A unit vector for the direction, which has a length of 1, and then whatever the force is, we just multiply by the force. If it's 10 newtons, it's just 10 multiplied by that direction. If it's 20 newtons, it's 20 newtons in that, sorry, not by that direction, in that direction. Okay? So again, a unit vector preserves the angle but keeps the length to 1, and it's a very, very, very useful thing to have when you do anything with physics, and there's other areas too where it's useful. Okay, so let's look at actually doing it for our example. So you can see here, remember we're calling our vector u, or we're also calling it AB. So remember we have this little cap. As soon as you see that, you know the magnitude is 1. All right, that's so you know that if I see this right here, I know that I've got a vector u, and I know that that this u cap has the same direction as u, but its length is only 1. Okay, so let's go through how to do these calculations. So the first thing is, how do you make a quotient worth 1? What do you need to do? The top and the bottom, what do they have to be? The top and the bottom. So if you want to make an answer worth 1, how do you do it? Got to make sure the top and the bottom are the same. That's the only way. So if you know the length of a vector is 6, you've got to divide it by 6 to convert the length to 1. So we're going to be doing this for vector AB, right? Vector AB. And so for this vector, we knew the magnitude was 6.71, right? And we know that this right here, which is actually the symbol for length, is 6.71. So what do I need to do to vector AB to turn the length into into 1? Well, I'm going to have to divide by 6.71. So here's the shortcut. So what I do, remember here, this is AB cap, okay, which is the unit vector. So if we remember, delta x was 6, delta y was 3. What I need to do now is to divide that by 6.71. Okay, I need to divide each of those by 6.71. That's dividing the whole vector by 6.71. What's 6.71? That's the length of the vector. Okay, that's the length of the vector. So now let's use our calculators and figure out what that is. So with our calculators, we can convert negative 6 divided by 6.71 to negative 0.894. 3 divided by 6.71 is going to be a little bit less than a half, right? 0.447. So now the angle will be the same. The angle will be the same because these are in proportion with these, right? Because we divided by a constant. Actually, something really interesting here is that this is going to be the cosine because it's related to x and it's a unit vector. Sine squared plus cos squared is 1. This right here is going to be the cosine of x, delta x, over r. And this right here is going to be the sine because it's y. Anyway, we'll talk more about that later. Okay, so what we want to do is, so this vector right here, it has the same angle as AB, the regular AB, but it has a length of 1. How could we double check and see? Well, how do we get the magnitude of a vector? We know that the magnitude is delta x squared plus delta y squared, and then take the square root, right? So I would have to do the square root of this and the square root of this. Let's double check and see if it is. So 0.894 squared plus 0.447 squared. And if I put that in a calculator, it ends up being 1. And the square root of 1 is 1. Okay. So how do we do this? How do we do this? Now there's a formula sheet on the next page we're briefly going to go over in a bit, but just remember that it is, this right here is your delta x, and this was your magnitude of the vector. This is your delta y, and this was the magnitude of the vector, right? The magnitude is defined by those absolute value bars. And that's how we got the unit vector. Okay, scalar multiples. So this is a phrase that's used. It's not, people don't understand what it is. I don't know why people don't say it, but so what we're going to do is we're going to take this vector and we're going to make a new vector. So we're going to take vector AB, the one that is negative 6, 3, and we're going to make it k times longer. Now, k times longer, if k was between 0 and 1, would be smaller, right? So that would scale it down. Well, we're going to make k, in this case, 2. Okay, we're going to have k equal 2, which scales it up. Now, what we call this k is a scalar multiple. Scalar because it scales the vector. Okay, again, it makes perfect sense to me, but it's something people, as soon as you say the word scalar multiple, which actually you'll use with matrices as well in university, but remember a scalar multiple is just a number. Vectors have direction and length. Scalars just have a number, okay? So there's no angle attached to a scalar. A scalar is just scaling something up or down. And well, it can be negative as positive as well, but it just doesn't have direction. It doesn't have an angle. Vectors have to have an angle measured from something. Okay, so we're going to make it k times the magnitude. So how do we write this? Well, so this time we're going to go back and we're going to focus on vector AB, except this time we're going to call it U again instead of AB. So what we're going to do is scale the vector by a factor of 2. We're going to call the new vector W. Okay, so if I want to make a vector longer, I have to scale delta x, but I also have to scale delta y, and I have to scale it by the same amount, right? The same amount. So here's the way we write it in mathematical terms. We say that the new vector w is equal to k, the scalar multiple, multiplied by the original vector u. In this case, we're making the scalar multiple 2. 2 times u. So w is the new vector, and we want to have it twice as long, or have twice the magnitude. It is going to have the same direction, by the way. So then what we can say is, well, what is u? Well, it's delta x comma delta y. So it's 2 multiples of delta x and delta y. So what were delta x and delta y? Delta x and delta y were -6, and 3. Now, it doesn't make sense if I think about this, right? If I'm scaling a vector, so here's a vector right here, and it has a certain delta x and a certain delta y. If I want to make this a bigger vector, twice as big, I have to scale both delta x and delta y, right? They have to be scaled, both of them. So that if I get a new vector and I wanted it to be twice as long, it would have to do that, right? So I have to multiply delta x by 2 and delta y. Otherwise, it wouldn't have the same angle, right? So if I'm multiplying delta x by 2, I have to multiply delta y by 2. Otherwise, I'm not going to have an equivalent fraction when I go to do trig, okay, tan, to get the angle. Okay, so it's going to be 2 times that -6, and it's going to be 2 times that 3. So -12 and 6. So this will have the same angle as u, but it's twice the magnitude, or twice as long. Okay. By the way, if your k value here, the scalar multiple, is a negative, it will just turn, so supposing we had a vector here, and we had a k value of -1, well, that new vector would be the same length, but it would point in the opposite direction. Okay, that's all. The angle would be the same, though. The angle would still be the same. Okay, well, actually, it wouldn't be. Sorry, it'd be off by 180 degrees. Okay, so last thing we're going to do here, adding and subtracting vectors. And in Cartesian form, this is so easy. Okay, we're going to take, and by the way, you're going to be doing all your work reading off charts, and the chart's going to show you point A, point B. It's going to tell you what k is, and then you're going to add or subtract a second vector. It might say add, it might say subtract. This one says add. And so we know that A comma B, our original vector, is -6 and 3. We have this new vector, BC, and it equals 7 comma -4. Okay, and what I'm supposed to do is, it says add, so I'm supposed to add those together. So AB plus BC equals -6 comma 3, +3, plus, and it can be minus, 7 comma -4. And then what does that equal? Well, all we have to remember is we combine x with x and y with y, right? This says delta x is -6. This says delta x is 7. Think of this as walking. If you walk to the left by 6, because that's negative, and then you walk to the right by 7, where do you end up? -6 plus 7 is 1. So your overall x will be 1. Okay, and if this was a minus sign here, you would just subtract, by the way. Then the next thing is, it says walk 3 up, and then since we're adding, walk 4 down. 3 up plus 4 down is 1 below, -1. Okay, and that's, so adding and subtracting vectors in Cartesian or algebraic form like this is really easy. Add the x components. By the way, that's what we call this, a component. An x component, this is a y component. Okay, and we're going to introduce in another couple of days z components. Okay, and so that's it, folks. That's that finishes out all the examples. I just want to tell you that on the next page, all the formulas are there for you, and so you can see the development of the formulas. So the only thing I'm going to do is to add in what they are. So I'll do that right now. You probably could just, fast forward and get the equations, but if you want to think of this as, so this is from P to Q, okay? And the tip is at Q, so we're starting at P and going to Q, and we're defining the location of P as x1, y1, and this one here is x2, y2. So if you look at this, what is delta x? Well, it's the x value up here minus the x value down here, and the y value is the y value at the tip minus the y value at the tail. Okay, that's important. Pythagorean theorem to get the length of a vector. Okay, that's fairly straightforward. Okay, this is the unit vector formulas. Okay, the unit vector formulas. So remember that we take the original vector u and we divide by the magnitude of u. Okay, so when I break that down, every original vector is defined the same way, delta x and delta y. What's the length of each vector? It's the square root of delta x squared plus delta y squared. So if I do delta x squared divided by the magnitude, delta y squared divided by the length of the magnitude, that's going to get me my new unit vector of length 1. Scalar multiples. So you can see here, if I start with this vector, u, it has a delta x and a delta y. If my scalar is 3, okay, my scalar is 3, what that means is I'm multiplying the length of this vector, maintaining the same direction, but I'm multiplying the length by a factor of 3. So that means equivalently I've got 3 vectors, right? If this would be, because it says here, 3u, so this is, let's mark this down, this is k equals 3, okay? So, and it's this right here, so that makes this 3u. But you can notice that if I take that in total and I make it a single vector instead of 3 vectors chained together, it looks like this, okay? But think about that again. I need 3 delta x's and 3 delta y's. That's what the picture looks like. Now, over here, we know that k times u is just going to be k times delta x and delta y. Then I multiply the k into the brackets, right? And it's going to be k delta x, k delta y is this new vector, k times u, which I might call another name. Last thing is adding and subtracting. I think for that one, don't worry about this diagram for now. We're going to deal with that a little bit later. That's more with geometric vectors. So hopefully you've done adding and subtracting of vectors geometrically in physics, if you've done that. And if you haven't done physics, well, yeah, that's a different story. But for now, we're going to focus on the algebraic vectors, and that's really, again, really easy. So if I wanted to take these 2 vectors and subtract them, what do? I just take the x values and I subtract those. So it's going to be 3 subtract 1. And then I take the y values and I subtract those. 6 minus negative 1. 6 minus negative 1, which is 7. 3 minus 1 is 2, and so that's the subtraction of the vectors, okay? Now, there is really important representations graphically, or what we say with geometric vectors. There's something called a triangle law for addition, a parallelogram law for addition. Those are really, 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 really important. We're not going to spend a lot of time with those because we're focusing on algebraic vectors and not geometric vectors. Okay, so that's how you do everything, add, subtract vectors. And so you're going to go through and there are questions on the next page. This is all the data here, okay? So question 1 is the one that I did. And then I would suggest you maybe just do 5, 6, 7, 8. That's it. That would be enough if you did those 4. And you did each part, right? So there's 5 parts, A, B, C, D, E. And getting this done will allow you, if you can do everything in here and do it quite fluently, then you're actually going to be able to do everything else that we do with vectors. But it's really important to get these foundational ideas and to get these foundational calculations that we use to measure vectors. Okay, so good luck. Please, please, please go through this. If you are someone who is going to have to take physics next year or linear algebra, you really have to do this stuff. If there's any chance you're going to do what's called linear algebra. And even people going into business, you may find that you have to take linear algebra will be a part. I know at Queen's and Commerce, linear algebra is a part of the math that they do. So you definitely want to go through this stuff and make sure you do a good job and really learn it, because this is foundational to what we'll do the rest of the unit. Okay, good luck, folks.